Hello everyone, welcome back to class. So before we go to technical details today, so there are three announcements. So I guess the first announcement is probably you have known that assignment 2 had passed, and the TA will use this week to grade the assignment, and hopefully can get back to you by next week. So the second announcement is assignment 3 will be posted tonight, and actually the deadline is still going to we are going to have 2 weeks for finishing assignment 3 here. So assignment 3, the deadline will be 3 p.m., like 2 weeks from now. That is going to be another Tuesday, and that is going to be, because today I think is October 18th, and this October, I think we have 31 days. So basically the deadline is going to be November the 1st. So please be careful, and also don't miss the deadline, which is going to be a deadline for assignment 3 here. So the third announcement is that the project proposal is due on October 30th. So that is going to be the end of week 8. So that is roughly speaking like approximately like 10 days from now. So you want to be careful also to take that deadline. So for that deadline, I think I have sent an email to announce that, and basically I uploaded a project proposal template on our homepage. So basically, please take a close look on that, and remember to also finish the project proposal deadline and actually finish it on time. Okay, so those are the three announcements that I'm going to give before the start of the class. So basically for today's lecture, we are going to talk about dynamic programming. So that is another very important class of algorithmic ideas that we are actually going to use when we want to design efficient algorithms. So let's first describe what is dynamic programming, and then we go with some examples. And actually today we are going to introduce at least 3 examples, like a weighted interval scheduling, segmented least squares, and also the knapsack problem. Okay, so let's start with like the general intuition about like dynamic programming. So in general, we have seen that basically for the strategies, so among the strategies of designing algorithms, so in general, we have mainly been seeing like 2 strategies. So first, we introduce greedy. So for greedy, the idea is that basically, I mean, we at each time we have our thoughts about what we are going to do next. So basically, I mean, in terms of like saying this a little bit more formally, that is basically we are actually building up solutions incrementally. I mean, or basically gradually, I mean, build up from like a initial answer, then finally, I mean, gradually to the whole solution that we want. And basically, we have some kind of a criteria that we are going to use. That basically, the greedy strategy is that basically at each step we are going to optimize some local criteria. So that is basically a very general thought about greedy. And basically, a second kind of algorithm that we have been introducing is divide and conquer. So for divide and conquer, basically, we break a problem. Basically, we break a large problem into, say, like a 2 or more subproblems. And actually, we solve each subproblem individually. And combine the solutions. To solve the original problem. So we can see that from like a general kind of methodology, a greedy and divide and conquer, they are actually quite different. And actually, a greedy is that basically you want to build up something, but you actually build up this gradually or incrementally here. And actually, divide and conquer is actually more like from like a top to bottom. That basically we have a large problem and we want to cut the problem into small pieces, and we have a good solution to the small pieces, and also we have good idea about how to merge them together, and then we basically solve the problem. So here, I mean, the strategy about like dynamic programming. I mean, this is probably, I mean, compared to gradient divide conquer, I would say this is probably not a little bit more like divide and conquer, that basically we also want to solve the problem. I mean, from top to bottom. I mean, we have like a large problem that we don't have a good solution. So in general, I mean, for some special problems, I mean, greedy really works. But actually, I mean, optimizing using some local criteria. Typically, for more difficult problem, I mean, we have seen examples that in general, I mean, greedy is probably not the best solution. So in general, have like a difficult problem. Maybe you want to, I mean, have like a good way to make the problem smaller and smaller. And maybe for like a really small problems, you have a good solution. Then you can like make them together to together solve a big problem. So basically, along this, we have divide and conquer, and we have been seeing examples along this. And actually, for a dynamic programming, we are going to say that here we actually break up a problem into a series of overlapping subproblems. And actually, we are going to build up those solutions. To larger and larger subproblems. Larger and larger subproblems. I mean, this is probably still a little bit abstract to understand, but in general, I mean, what is being like dynamic programming here? So the thing is, being dynamics is that in general, I mean, a main difference between dynamic programming and divide and conquer is that this is really somehow we want to plan overhead. So it's not, I mean, maybe for instance, in divide and conquer, we just have this problem and we cut in the middle. So here, for dynamic programming in general, we want to somehow utilize the structure of the problem. Maybe it is definitely not here cut in the middle, I mean, in most cases. But in general, we know that a certain problem, I mean, if we want to solve that, it definitely has some kind of structure that we actually use. And basically utilizing this, and we know that such kind of problem, we need to have such kind of plan. And then basically we plan over time. And basically we can use such kind of algorithm to solve the corresponding problem. So this is, I mean, this is really like a very abstract understanding about like what is dynamic programming and basically what is the strategy that we are going to talk about. I mean, this is probably a little bit too dry, but let's actually, I mean, having this kind of general intuitions, let's actually go into some specific problems. So the first problem that we are going to talk about today is a weighted interval scheduling. I guess this is probably going to be something you're familiar with because I mean, when we talk about greedy algorithm, we have been talking about the interval scheduling problem. But nevertheless, I think we can actually consider like a more generalized version, which is the weighted version. So what is the corresponding definition? So let's give the statement here. So the job J here. So basically, we start at time Sj and finishes at, or let's say Fj, and has weight, let's say, or value Ej. So similar to the interval, I mean, unweighted version, interval scheduling problem. So we say that two jobs are compatible if they don't overlap. This is looking so good. And the goal here, so the goal here is a little bit different compared to the unweighted integral scheduling problem. So here we are going to find the maximum weight subset of mutually compatible jobs. Okay, so you probably see the main difference here. I mean, for the unweighted interval scheduling problem, so we don't have the weight here. I mean, or you can say that all the weight, I mean, all the intervals, they have weight one here. I think that is basically an equivalent way to say this. And in general, we want to find the maximum weight subset. I mean, for the unweighted version, if the weight of all the intervals, they are exactly one, I mean, this is just equivalent to find like the largest number of intervals that they don't overlap with or we say that they are actually mutually compatible. So basically, we here consider like a more advanced version that we allowed the intervals to have weights. In general, we want to think about how we can now give a good algorithm for solving this weighted interval scheduling. So let's actually, since I've been talking about this all the way here, so recall the greedy algorithm works if all weights are. And actually, I'll recall that the strategy we use, let's use the red color here. So the previous strategy, I mean, in general, as we have been mentioning, I mean, we want to talk about greedy algorithm, but greedy in what? I mean, you have some kind of basically a strategy that you need to have, and basically you need to optimize according to some local criteria. So that is basically the part of the greedy. And actually, for the interval scheduling problem, we have seen a lot of like a different greedy strategy that actually fail. So basically, we have like a specific design here, and basically for the greedy strategy for the interval scheduling problem, we actually consider jobs. We actually consider jobs in ascending order of finishing time. And basically, at that part, basically after having this kind of ascending order in terms of finishing time, we just add job to the subset. If it is compatible with previously chosen jobs. So this is just a very quick recap about what we have been talking about for this interval scheduling problem when we can actually use the greedy strategies to solve that. But I think here, I mean, since we are talking about the weighted version of the problem, one observation that we can make is that basically a greedy algorithm can actually fail. And actually, yeah, in a significant sense, or we say spectacularly, if arbitrary weights are allowed. So why is that the case? So because here we are picking intervals according to their finish time. So let's say that we have an early interval, basically weight equals to 1. But what if you have like a much longer interval, but also much larger weight, say weight equals to 10? I mean, in this case, if you just originally use this greedy algorithm, you will pick this one. And after picking this one, this is not going to be compatible with the second interval, and basically you finish the algorithm. But unfortunately, the interval that you are picking here, it only has weight 1, and actually the optimal solution here has weight 10 here. So this is a significant difference. I mean, at least, I mean, maybe this a greedy strategy, it is still somehow helpful, but at least we need to make some adaptation to make sure that, I mean, even for the weighted interval scheduling problem, we can still give a good algorithm for that. Okay, so any quick questions about the definition of the weighted interval scheduling problem and the issue that we are, I mean, we cannot at least originally use the original greedy algorithm to solve that. Okay, so if there is no question, let's think about, I mean, maybe this greedy algorithm is not totally useless, but I mean, we have to make some changes. So basically think about what we can actually do at the moment. So let's view, we can make some notation here. And then we can introduce the new idea. Maybe after thinking about this, what is the right strategy that we are probably going to utilize? So notation. So basically we label jobs by finishing time. So let's, without loss of generality, say that F1 is smaller than F2, smaller than Fn. That is to say that basically, this is just kind of an order issue. In general, you can just apply a sorting. But without loss of generality, we assume that the first job is finished earlier than the second, finished earlier than the third, etc. The Fn, the last job is finished at last. Okay, so this is just for our ease that we want to define a certain notation here. So basically, we define a function called pj, which is actually the largest index I, actually strictly smaller than j, such that job I is compatible with j. So what do I mean by that? So maybe let's actually see an example here. So this is going to be the time axis, and basically we're going to have some intervals here. Let's actually make this a little bit. Like this. So I think maybe let me draw some kind of dashed lines to make this clear about like the length of the intervals. So let's assume that maybe we have a certain task, and maybe, for instance, the last job finishes at the time 11 here, and maybe we can select intervals here. So basically, as we just mentioned, we label jobs by their finishing time. So maybe, for instance, like the first, let's assume that the first job finished at time 4. So maybe, for instance, we can assume that maybe this is job 1 here, and maybe, for instance, this is job 2. I guess maybe let me actually use the red color to make it look more clear. So this is 1. This is 2. Let's maybe assume that this is 3. We want to see some cases where it is a little bit complicated. So let's assume that the job 3, although it finishes quite late, but actually it starts quite early. So let's assume this is 3, and this is 4. Maybe this is 5. And this is 6. Maybe this is 7. Let's just say like we have like a certain problem like this. So what is P7? So let's check this definition here. So P7 is the largest index I. It's strictly smaller than 7. The mean I is at most 6 here, such that job I is actually compatible with job J here. So basically here, the 6th job. So basically this 6th job, it is not compatible with the 7th job, but the 5th job does. So basically we can say that P7 equals to 5. So what is, for instance, let's maybe say like, what is the value of P5? So here, unfortunately, I should probably make like a further explanation here. If no such index exists, we say Pj equals to 0. Here it's just like P5 going to equal to 0, because we can clearly see, because we're talking about the index that is smaller than 5 here. But unfortunately, I think 1, 2, 3, 4 here, none of them are compatible with P5 here. So this is just like for the safety of notation here, we can basically see that P5 equals to 0. And in this case, we just like, if no such index exists, we just make such kind of notation here. So about how about like maybe let's say P4. What is the value of P4? Yes. So the value of P4 here is equal to 1 because the third job is not compatible with the fourth job. And actually the second job is also not compatible with the fourth job, but the first job does. So basically P4 equals 2. So basically, in terms of this, you can clearly see, I mean, this P function is a little bit evolved. I mean, it is probably not like a monotone increasing or decreasing or whatever function. So this is basically something we want to be careful about. But nevertheless, I mean, in general, I mean, after we have like a sorting, I mean, we have sorted all the intervals here. So determine, I mean, all the values of P here is basically not something that is going to be very expensive. So this is later we will explain this. So here we have this kind of, I mean, we have the knowledge of these intervals, and we have this P function. I mean, in general, we want to talk about like the optimal solution. I mean, the output that has the maximum weighted and basically maximum weighted intervals. So basically, I mean, it sounds like a little bit evolved problem. So maybe let's just directly go into. I mean, we just define what is the optimal solution here. So we define optimal. I mean, this kind of dynamic programming, as we just mentioned, I mean, here, I mean, a little bit weak way, I mean, the strategy that we are going to use here. So somehow it is still a little bit like the divide and conquer problem, that we have a larger problem. We basically want to reduce this to smaller and smaller problem. So here, if we want to consider, like, I mean, we want to take a close look at the solution. I mean, what is the optimal solution ought to have? I mean, what is the corresponding structure here? So this is also going to be parameterized. I mean, in general, we want to maybe we want to define like optimal of J here, where this is actually going to be the value of optimal solutions. No, I mean, maybe not as here. In general, optimal solution to the problem. Consistent of job requests from 1 to J. So the parameter here that we are going to use is depending on the jobs. I mean, of course, we can see that the solution, the solution that we should output is basically OPT of n here. But in general, we can have like a series of definition. I mean, basically, we have this OPT of J equals to the value of the optimal solution to the job, that if we only consider the first J intervals. And basically, hopefully, we can have like a good relationship to build up. I mean, basically, we want to figure out what is the relationship between different J's, between different OPT J's. And basically, this is probably something we want to have a good understanding. Okay, I guess this is still more like a definition kind of thing. So maybe let's think a little bit more. I mean, let's actually delve into this and think about what is actually the strategy. I mean, what is going to happen for this optimal solution? Okay, so in terms of OPTJ here, it only has 2 scenarios. Oh, I think I made the wrong spelling here. Scenarios. It chooses job J, or it doesn't choose job J. I guess this is just a trivial sentence. I mean, if you consider like optimal solution with J here, I mean, either it has job J or it hasn't. I mean, this is trivial, but what I'm saying next, it is not going to be a trivial here. So let's actually take a close look about what is going to happen in these 2 scenarios. So basically, we say that the case 1 here, the case 1 here is that OPT selects object. So in this case, what is going to happen? I mean, let's think about, I mean, for instance, according to the definition PJ. So PJ is actually the largest index such that the job I is incompatible with J here. So in this case, I mean, just according to this definition, we just know that we can't use incompatible jobs. I mean, from PJ plus 1 pj plus 2 all until j minus 1. So this is just according to the definition of pj here, because pj is the largest index such that the drop I is compatible with j here. I mean pj plus 1 is larger than pj. And it is actually not the value of pj here. So we must have the information that pj plus 1 and actually pj plus 2 until j minus 1, they are actually incompatible with the drop j here. So I see there is a question. The question, what if there are several compatible jobs? There is like an ordering here. We actually make the order of all the finished jobs. Here, basically you can see that I'm actually being very cautious here that the finishing time of F1 is actually smaller than F2, smaller than F3, etc. There can be situations that you have the same finished jobs. In that case, we just like pick arbitrarily. But actually, when we look at this, we just go from like the, according to this index rule. For instance, we are talking about the P7 here. You just check the sixth job. The sixth job is incompatible with the seventh, and then you go to the fifth. Actually, the fifth job is good. So I guess it's clear to you now. There can be a lot of compatible jobs, but you just you have this kind of indexing, and you just like go from the intervals that if from according to their finishing time, you just like make such kind of checks. But actually, a very important observation here. So here, for example, the right, yes. So it is possible. If you have algorithm, here, for instance, the first job is compatible with the eighth, but you don't want to get everything messed up. You want to have like a strategy that hopefully this is going to help you. I'm probably going to continue to introduce what is the algorithm here. Basically this algorithm for the weighted interval scheduling problem. But in general, basically the strategy here, we will look at the finishing time, and basically we will see that looking at the finishing time, it is helpful because you have this kind of structure of the OPTJ that you can actually use here. Okay, so here, the point is that basically according to this definition of P's here, we clearly see that we basically cannot use the jobs pj plus 1 or pj plus 2 until j minus 1 because they're actually incompatible with the interval the job j here that we are actually choosing here. So this is basically suggesting that actually if we have like optimal solutions here, basically we must include the optimal solution to problem consisting of remaining compatible jobs. Basically from 1 and 2 until pj. So because at this point, this is also a very important observation here, because as long as the fifth job, it is compatible with the seventh, because we know that P7 equals to 5. The fourth job, the third job, until the first job, you look at back, they must also be compatible with the seventh job. This is basically because of a relationship like this. So we know that for intervals, basically we have a start time. This is basically like SI and end time. Fi. So basically we know that Pj is compatible with drop j. This is actually going to imply that the finishing time of Pj is actually smaller than Sj. That is basically here, the fifth job, it actually finishes, earlier than or equal to the start time of the seventh job. But actually we know that according to this rule, basically F1, F2, all until Fpj, it should all be smaller than Sj, because we actually arranged all the intervals according to their finishing time. And actually, this also should suggest that 1, 2, until pj is compatible. So any questions here? So this probably is also going to address like a question asked by one of the students. So basically, I mean, you have the freedom here. I mean, here, for instance, maybe pj equals to 5, I can pick the third interval. But this is just going to ruin the structure of the problem. But in general, I mean, the very cute thing about like considering this kind of like a case discussion is that, so basically, we know that we definitely cannot pick the intervals pj plus 1, pj plus 2 until j minus 1. But you do, I mean, after having picked the job J here, you don't have any further restrictions on the early intervals. I mean, until the interval 1, interval 2, until the interval pj. So that is basically saying that, I mean, in general, we are talking about the optimal solutions that we are going to use here. I mean, in general, I mean, the optimal solution, it definitely has two cases. I mean, this sentence, it is like a trivial sentence. I mean, it either chooses job J or it doesn't. But as long as if your optimal solution, it chooses job J here, I mean, basically we are pretty sure that we can actually, basically, we don't have any further restriction on the interval, basically drop 1, drop 2 until drop pj here. So basically in this case, we know the OPT of J is actually going to be equal to, I mean, we have chosen the jth interval, and actually this gives you some value here. Basically, you have the Vj here, and actually you are going to have the Vj plus OPT of Pj here. So this is basically the thing that we are going to have for this case. So basically, any questions for this case 1 here that OPT select structure? Okay, so maybe let me actually finish like the discussion for the second case, and maybe let's look together what we are having here, and hopefully maybe if you have any questions, I can just feel free to ask. So basically for the second case, I mean, of course, for the second case, the situation that we are going to deal with is that the OPT does not select. I mean, in this case, the only information we know is basically this sentence that OPT does not select job J here. But the thing that we know that is OPTJ here is actually going to equal to OPTJ minus 1. Because you are talking about you want to solve the optimal solution using the intervals 1, 2 to J here. And you know that you are not actually going to choose the jth job here. Then definitely you know that OPTJ just equals to OPTJ. Or in general, I mean, as a summary, I mean, looking at these two cases, what is actually the solution that we are going to have here? We are actually going to know that OPTJ, it is actually going to be 0. I mean, of course, if J equals to 0, I mean, at the very bottom, if you don't have any intervals, you don't have any value. So the OPTJ, when J equals to 0, it actually equals to 0. But actually, we can, I mean, very importantly, I mean, we can think about what is the strategy. I mean, after we have like jth interval, the interval from 1, 2 until j here. So basically, that really depends on whether we are going to use the jth interval or not. So basically, we get like a recurrence here. So we can say that OPTJ here, it should equal to the maximum of Vj plus the OPT of Pj of the OPT j minus 1. For all j larger than 0. I guess there is a bracket here. So this is basically a very important recurrence that we know that in general, as long as we have j intervals, I mean, basically, I mean, for this weighted interval scheduling problem, and you arrange all these intervals according to using like ascending order of their finishing time, you know that we are going to have this kind of recurrence. I mean, it might be the case that, for instance, like Vj plus OPT Pj, it is larger than OPTJ minus 1. I mean, in that case, I mean, you should pick the jth interval, and basically, because the strategy that, of this picking the jth interval and using the rest, and basically that is calling the OPT of Pj. I mean, this is going to be better than OPT of j minus 1. I mean, if the former one, this Vj of OPT Pj is larger than OPT j minus 1. On the other hand, I mean, if this picking this interval is too, I mean, it's too bad. I mean, in general, for instance, if Vj plus OPT Pj is smaller than OPT j minus 1, you just shouldn't pick that and actually call the solution just using intervals from the first interval to the j minus 1th interval. So this is basically a recurrence that we know that for this specific weighted interval scheduling problem, we must have this kind of recurrence relationship for the optimal solutions. Okay, so any questions for this? I guess this is an important point, and actually, based on like a little bit trivial observation that OPTJ either chooses substrate or it doesn't choose. But nevertheless, I mean, for the two cases, we know that we are going to have such kind of relationship. So, is there any question for this? Okay. So basically, you see that, I mean, this kind of strategy, somehow it has a little bit similarity to either divide and conquer or the greedy, because here it is somehow still like a greedy way kind of argument that in general, I mean, we want to talk about optimal solution and basically we want to think about how we can utilize using the structure of the optimal solution. But also on the other hand, it also has a little bit similarity to divide and conquer because we are actually dividing the problem. Although in some kind of sense, this dividing the problem is also in like a greedy kind of sense. I mean, this is really a little bit tricky, but in general, I mean, such kind of strategy that in general you have like a problem and you take a close look at this optimal solution and think about this structure and basically divide it into subproblem. And this is in general called dynamic programming. And basically the main focus that we are going to talk about today and also in the next lecture. Okay, so if you don't have any further questions about this recurrence relationship, I mean, the next thing is that we need to think about how to solve this, and basically we need to give an algorithm for that. So let's think about an algorithm here for this problem. So an algorithm that we can consider is that, I mean, the input is going to be, I mean, n here are the starting times, the finishing times, and also the values of the intervals. So according to our algorithm, we are going to, the first step we are going to do is that we are going to sort. So basically we are going to sort jobs by finishing times. So that F1 is smaller than F2, smaller than or equal to Fn here. And the next thing that we need to do is that we need to compute all these values of P. So basically compute P1, P2, until Pn here. So the recurrence part, I mean, we can just write down this. I mean, we know that the optimal values, they have such kind of recursive relationship. So we can call this as like a function, compute OPTJ. OPTJ. So basically, we just honestly write this down. I mean, if j equals to 0, return. Just returns 0. And if else should say else, I mean, it just means j is larger than 0. We just return the max of Vj plus OPT Tj and OPTJ minus 1. So this is going to be our algorithm. So any questions for those? So this is just like a direct way that we write down this algorithm. I mean, we have these values and basically we just compute this and we just we call this relationship. But actually, maybe if we take a close look at this, there are actually some issues with this kind of algorithm. So, I mean, maybe you can think about, I mean, what can be like a potential problem if we actually run this algorithm. So do you have any? Yes, yes. So actually, one issue, as actually Bo had mentioned, is that in general, the recurrence can be quite expensive here. So why is this the case? So let's, for instance, think about this relationship. For instance, let's assume that maybe we have like an instance, we have such kind of interval. So maybe we have, this is our interval, the first interval, and maybe, for instance, this is the second, and maybe this is the third, maybe this is the fourth, and maybe this is the fifth. So basically for this instance, you can clearly see, I mean, basically P1 equals to 0. And also on the other hand, we know that P2 also equals to 0. And basically, on the other hand, P3, oh, I think my drawing is a little bit, I think I'm actually probably make this a little bit, or nevertheless, let's maybe, let's move this a little bit. I guess I think I want to make the points in the middle, but somehow it shifts this a little bit. So I guess let's consider this. I guess this is also looking a little bit better. Yes. Yeah, I guess, yeah, this is probably what I really want to talk about. Yes. So here, let's consider a case where, the previous interval, their starting time is actually at the middle of the starting time of the current interval is actually at the middle of the previous interval, and actually all the intervals, they have the same length. So in this case, we know that, of course, P1 equals to 0, P2 equals to 0. And in general, you can actually have further intervals along this kind of definitions. But in general, you can see that Pj equals to j minus 2 if j is actually larger than 2. So actually, clearly here, P3 equals to 1, P4 equals to 2, and P5 equals to 3. So let's just think about actually what is going to happen. If you just run this algorithm, what is the situation here? Let's actually draw a tree here. For instance, we consider a case where j equals to 5. So for j equals to 5, we are basically going to return. So basically, when j equals to 5, we are actually just going to return the maximum of Vj plus OPT. The P5 here equals to 3 here. So that is going to be like OPT3. And actually here, j minus 1 and j equals to 5. And actually we are going to have OPT4 here. So basically we can say that we can consider like a tree here. From 5 here, on the one hand, we need to solve a problem of size 4 here. And actually on the other hand, we need to solve a problem of size 3 here. So basically, we have like a problem of size 4 and also problem of size 3 here. So we need to further go into this. How about j equals to 4? In that case, we are going to return the maximum of Vj plus OPT. Because we know that P4 equals to 2 here. So this is actually OPT4, and actually j minus 1 and j equals to 4 here, and this is actually OPT3. And similarly, we can clearly see that for j equals to 3, we are actually going to return the max of Vj plus OPT1 and OPT2. And nevertheless, for j equals to 2 here, we are going to return the max, of Vj. OPT0 is 0, so we can just get relaxed at OPTj. OPT1 here. And of course, when j equals to 1, return the max of Vj OPT0. In this case, j just equals to 1. OPT0 equals to 0, so we are good. And actually this equals to 1. But using this kind of recurrence relationship, from 4 here, here it actually also has children. This is like a 3 here, there is a 2 here. For the 3 here, you have like a 2 here, you have a 1 here, you have a 2 here, you have a 1 here. And basically you have a 1 here, you have a 0 here. I guess I won't further draw the 1 here because for the 1 here, it's corresponding solution like this. And basically here you have a 1 here, you have a 0 here, 0. So this is, in general, just imagine, the length of such kind of trees. If you just write an algorithm like this, so this is like the most intuitive way, the most direct way that you want to write down a dynamic programming algorithm. But actually, if you run this algorithm on a computer, this is going to be a disaster because this is actually in general the cost is going to be super expensive. As actually in general, it is mentioned that the cost of this kind of recursions can be actually exponentially large. In the worst case, it can be like around 2 to the n. So this is definitely something, not something we want. And actually, we can imagine that this is basically this recurrence is really not necessary because actually this is a lot of things that are just like repetitive. I mean, a lot of things are repeated for a lot of time because I mean, there is actually just no difference between this one, and actually no difference between this two and this two here. Because you are talking about OPT1, OPT2, OPT3, etc. I mean, this does not really change, I mean, along the way here. So actually, this is not something that is super difficult to be fixed. I mean, this is just a standard trick, and actually mentioning this kind of like issue is just like to make sure that we are writing down a dynamic programming algorithm whose time complexity is also what we want, and actually does not have all this kind of repetitive issue. And actually, the solution that we can clearly see is that this is called memoization. So what does this mean? It's just that you store results of each subproblem in a cache. Lookup as needed. So if we don't do this, I mean, we just like we mark this as the exponential time in the worst case. So we definitely don't want this happen. And in general, we want to utilize a trick called memoization that in general, we can store a result of each subproblem in a cache. So what do I mean by that? So let's take a close look at this algorithm. So I guess, I mean, here I can call this algorithm as the brute force algorithm, which is, I mean, very intuitive. You just use the recurrence here, but unfortunately, this is not the best idea. But nevertheless, there is a very easy fix on this. We call this algorithm memoization. So the input, it is still going to be n S1 to Sn, and of course, all the finishing times, and also all the values. So I guess we can actually copy maybe, let me just using copy and paste for the first two lines. I mean, this is of course something we need to finish at first. We need to sort the jobs by their finishing time so that F1 is at most F2, at most Fn, etc. And actually, we need to compute all these values of P's here. So the next thing that is going to be different, I mean, instead of, I mean, just like we're brute forcefully computing all the recurrence here, we can actually maintain a table. So for j from 1 to n, we just initialize mj to be empty. So we have this table M to actually save all the values. I mean, if it needed, we can just look up the table with instead of just calling the recurrence here. So we set M0 to be 0. I mean, this is just saying that OPT0 is just 0 because you just cannot pick any interval here. So we call this as an M compute OPTJ, where if MJ is empty, I mean, if we encounter a certain case where the entry of the table is empty, I mean, in this case, you should definitely, I mean, make the computation. You can actually call the recursions. I mean, that is the situation where we set the value of mj equals to the max of bj plus m compute OPTJ. I mean, we definitely, OPTPJ, sorry. We definitely need to have some kind of recurrence, but only if needed. I mean, of course, if the current entry of the MJ is empty, you definitely need to make such kind of calculation. I mean, you just compute the maximum of VJ plus M compute OPT. This is basically, we say that, excuse me. So here, it is basically where the recurrence happens. And they are actually going to, on the other hand, of course, in the other case, we need to M compute OPT of j minus 1 if we don't choose the interval j here. So this is basically the place we need to use the recurrence. But nevertheless, I mean, in the other case, I mean, maybe let me also mark this if as the red color. So else, I mean, for the else case, it just means that MJ is not empty. I mean, we don't need to make further recurrence. We just return MJ. Okay, I guess you can probably see the intuition that basically we use like a table M here to store the values that we compute along. And actually, since we can actually take a break for 10 minutes, and after we take the break, we can continue to talk about the details of this.